Hello everyone. Sorry for the short delay. We can thank the awesome Wi-Fi. But okay, let me introduce the speaker today. So we have the pleasure to have Alexander Vikman. He did his PhD in Munich in 2007 with under the supervision of Slava Mukhanov, and then he did a postdoc in NYU in New York. Then another one at CERN. He was a fellow there, CERN, Stanford, in Munich then, and now then he became a senior researcher at Institute of Physics in Czech Academy of Sciences in Prague in 2015, and he's a JSPS fellow and a member of JCAP editorial board since 2017. So without further ado, the stage is all yours.
Okay, so thanks a lot for the invitation and for this kind of introduction. It's my great pleasure to be here and to give this seminar. Unfortunately, it got postponed because I managed to break my leg before. It's my first time to Portugal, so I'm enjoying so far a lot. So really great place. Thanks a lot. I'm trying to entertain you on talking about this mystic subject, how one can live with ghosts in a stable way. So please feel free to interrupt at whatever moment of time and ask questions, and I will try to address them in the best fashion. Okay, now let's see whether it will work. Okay, let's try to do this. And this also would not work in the case.
Sometimes it happens that it starts working, then it stops. Like we
So you see, it's hard to diffuse ghosts. That's a proof, right? Okay, what should I do? Reboot. That's not.
Stop sharing and sharing.
Not a good idea. Okay.
I think the problem is he doesn't have a mouse.
No, it's good, but it's all just frozen. That's the problem. Very good. Oh, suddenly, okay, I don't know. So basically, this talk is based on this. I don't know what happened. This talk is based on this paper, which I wrote with Shinji Mukayama, and it's a PRL. That's already like 2 years old. It's one paper where we first have done the first model on this type, and then like what happened? It just does not follow anything. This doesn't move. Okay. Okay. Probably this works. Okay. Let's see. So, and then a second paper is this one. It's more fresh. It's actually kind of published already. In reality, it's just accepted, but we are waiting till the special issue of JCAP appears online. So feel free to look at these two papers if you want to see more details. And actually, see, I abused the title of this great paper by late Stephen Hawking and Thomas Hertek. So it was called Living with Ghosts. And if you want, that's one of my primary motivations. What they say, perturbation theory for gravity in dimensions greater than 2 requires higher derivatives in the pre-action. Higher derivatives seem to lead to ghosts. And then what they say, that's what I don't like. That's not what I'm going to do, because they say that ghosts are states with negative norm. So in that sense, what we are going to do is not that kind of living with ghosts. Okay, it's slightly different. Namely, my definition is the following: ghosts are dynamical degrees of freedom with negative mass, or if you want, with negative kinetic energy, or better even to say kinetic energy which is unbounded from below. And then, of course, that looks quite pathological, and you would ask, in that case, why should we care at all? Okay. And let me provide you my personal list of motivation. You feel free to enlarge it or cut it if you want. So why should we be interested in ghosts, or can we be interested in ghosts? So first of all, by education, I'm a cosmologist. So what we have is an interesting cosmology. For example, we could have phantom dark energy, which is still not forbidden. Of course, there are other ways actually to make phantom dark energy without having ghosts, but ghosts is the standard realization of phantom dark energy. And that would actually give you a super accelerated universe with growing Hubble parameter over time. Second thing is bouncing universes. Okay, for that we clearly also need Hubble growing with time. So bouncing universes is kind of also interesting story for initial conditions in the universe and so on. Purely phenomenologically interesting thing, inflation with blue spectrum of gravity waves. That's another interesting manifestation of ghosts. Then following Hawking and Hertog, what one could say is another motivation is that generic high derivative systems have ghosts due to Ostrogradsky theorem. And you know, I'm embarrassed to quote somebody from 1848. And as you see, this one is purely phenomenological motivation, right? And maybe except of bounces, which is more kind of ideological question. However, this one is more like ideological paradigm question. Why equations of motion should be always second order, not higher order. And it's related to the point that also actually third order equations of motion is the simplest example of chaotic system, okay? Because the minimal number of space dimensions which you need are 3, and in that case you could organize chaos. Surprisingly, such things are used in what is called Chua circuit. So that's a proper random generator. Okay, so it's really a way to generate chaos. Then,
Can I?
Yeah.
Proper random
probably. I don't know. Look, I'm not a specialist. I was surprised that this thing is used there. You see, if I were doing random generators, that would be great.
Yes.
So then, you see, the thing is that what Hawking was quoting is similar to this result, that actually renormalization or quantization of gravity implies appearance of high order operators. Surprisingly, if you write these two terms additionally to normal Einstein protection, so namely Ricci scalar squared and wild tensor squared, in that case, gravity can be actually renormalizable. Okay, this is quite an interesting result obtained by Kellogg Stelly before I was born, and necessary such an action would have ghosts. Okay, that's an interesting story as well. Then there are more ideological questions. You know, if you allow for negative energies, what to do with entropy, thermodynamics, thermodynamical stability, and things like that. More interesting thing which you cannot see, you see the system doesn't like it. It's probably aliens who control it. So is it possible to screen gravity? Don't forget that, you know, gravity is the weakest force. Actually, the real force which we abuse in our everyday life is electromagnetic force. But actually what we have is only remnants of electromagnetic force, because usually it's almost totally screened. Okay? So if we're able to screen gravitational force, we will have it in our hands, in our disposal, we will have it under control. We will do all possible crazy things like interstellar travel and so on. Okay? So that's really would be great for technology, probably not in my lifespan. Then, especially here in this group, I should not remind you that opportunity to have stable ghosts would imply that one could have interesting exotic compact objects like wormholes. And then, you know, similarly to the previous point is, if you can screen gravity, then maybe you can also screen cosmological constant, or maybe at least you can screen cosmological constant or vacuum energy. And this is very important because we have no idea how to obtain the number which we see in observations. And then also more theoretical question whether gravitons can be massive. And you see there is a huge literature on that. And usual simple construction of massive gravitons, let's say Fritz-Pauli action from 1930s, would imply that if you go beyond Minkowski, the system becomes ghosty. And that's infamous Boulevard Desert Ghost from 1972. And then this was kind of solved by DRGT, by Claudia Duram, Giga Gabadadze, and Andrew Tolley. But it's only partially solved because in reality, if you go outside of Minkowski, then two modes, as far as I remember, become actually also ghosts. So they killed the 6th degree of freedom, which was this Boulevard Desert Ghost. But out of the 5 degrees of freedom, 2 are not really healthy if you go to cosmology. So that's actually pretty interesting question. What can be there theoretically, and what to do if there is a ghost? Unfortunately, I have never seen any calculation whether this, how pathological are this or this ghosts. So basically, what is the rate of instability which can they cause? Okay, you can feel free to enlarge the list or cut the list off, and I will be strongly, dependent on this guy. By the way, do you know this guy? Who is he? Do you recognize him? No. Another attempt?
The French guy.
You're right, but only partially. Because I can show you his name, even though it will be covered by this nice screen. Actually, okay, you can already get that he's Lagrange. So it's basically Lagrange. He was originally Italian from Piemonte, and that was his kind of true name. So, but of course, if you don't recognize this guy, you would not recognize the next guy. But what I'm going to talk about is Lagrange stability. And that's the notion I actually never knew, but my French colleagues, especially Cedric, they knew what is Lagrange stability. And actually, it's a very simple statement that the motion is finite. Okay, so it's always bounded in a finite region of phase space. Okay, imagine you have a potential well which increases up to infinity, then you are trapped in this well. You never leave. Okay, that's an example of a motion which is Lagrange stable. Sometimes it's also called globally stable. There are different notions of stability, and interestingly enough, Lagrange stability doesn't apply another type of stability which is related to this one. But now it works. So you probably would not recognize this guy, but I will give you a hint. This is Lyapunov, and Lyapunov introduced the most modern knowledge of stability, which is actually a very simple one. So Lyapunov stability means that if I take two solutions which are close by, they can stay close up to infinity in time. Okay, so that implies that for every two solutions, basically, I take at the beginning by some norm which I choose some epsilon, and for arbitrary small epsilon, arbitrary far away in the evolution, I can choose sufficiently close initial conditions so that it will be there. Okay.
Over there in the Lagrange, use and contact times the cycle.
I could speak, but I will not.
Is the system ergodic when you're in the Lagrange?
Actually, that's a good question whether this system is ergodic. I actually don't think so, but we should discuss it later. I don't think our system is ergodic, actually. Perfect. Perfect. So now let's see this. So let me, yeah.
So about the stability, so you pay whatever. Does that really
Yes. Absolutely. 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 And that actually implies that the equation should not be singular, because if they're singular, then there's no infinity. Okay. Very good. Now let me remind you of Strugatsky theorem. So basically, let me tell you a modern version for poor people. We poor people would write a propagator. This propagator has, let's say, mass scale, and it has 4 momentum power 4. And this propagator you can just write as sum of 2 propagators, and one has a negative sign. And this is the key problem of such a dynamics or optimization of such systems. So this is due to Strugatsky. And as a true Russian, or maybe now one should say Ukrainian, I don't know. He would be probably surprised if somebody would talk in Ukrainian. But he was also originally actually from Poltava and studied first in Kharkov. Well, then he moved to Paris, and as a true Russian, he was writing everything in French. And my French collaborators are claiming that in this paper, he was actually rederiving whole Hamiltonian dynamics from scratch just for high derivative systems, because he could not read English, and therefore he didn't know about it. So now you see, you can save a lot of time if you learn languages. So basically, a very simple point. You take Lagrangian, which depends on Q, Q dot, and acceleration. In that case, you introduce canonical momentum for your coordinate Q. And you see, surprisingly, this kind of long expression, which you unfortunately cannot see due to the screen. But this expression contains Q3 dot. Note that here there is no Q3 dot. And then you introduce a canonical momentum for the neighboring variable. You see, q dot are now not canonically conjugated as a normal linear case, but now it's a second independent variable. And you introduce momentum, then you introduce standard Hamiltonian. What is most important here is the following, that because this P1 is related not to the velocity, but to third derivative, and third derivative is not in the Lagrange, suddenly you see that this P1 appears only here linearly. That implies I can have infinitely large, infinitely small p, I couple to the system, and I will explore everything. Okay. So now let me see mechanical analogy of Gauss. This linear term in momentum, you could do some simple canonical transformation and write as negative kinetic term. Let me remind you, in oscillators, that's practically the only thing we all can do. Some of us very well, some of us less perfect, but so in reality, if you compare it with cosmological perturbations, that's a typical, thing where we study Gauss. So this is perturbation action. It has two free functions, z and c. They both depend on time. Take now each mode. Each mode now is an oscillator where this z plays the role of mass in mechanics, csk plays the role of omega. Okay. So now Gauss and gradient instabilities for this action are very easy. So first, gradient instability, that's oscillator inverted potential, Cs squared less than 0, exponential growth. What is most important, contrary to an oscillator, it will be growth with the rate of instability proportional to k. So the shorter is k, the faster is the instability. That's deadly example of, if you want, a Adamar example of ill-defined evolution equations. Okay, another one is Gauss. So Gauss is just this z less than 0. If you look at linear analysis, nothing happens. It's just stable, nothing bad. However, of course, you need to couple this to gravity, and then, for example, you can write the simplest diagram. Two gammas out of vacuum, two photons, and two of these perturbations, and let's suppose the simplest case, z is -1, and they're coupled through just normal 1 over m Planck. Okay?
Then only the time data, only the time data comes into sign and it goes to calculation.
Everything. Because I want to disentangle Gauss instabilities which are purely due to interactions from instabilities which would appear on linear level. So therefore, I put this, if you want, the negative sign in front of whole action, or if you want whole Hamiltonian. Good point. So now here I have in this vertex 1 over m, here 1 over m, total guy, the amplitude 1 over m squared. Then therefore the rate of instability squares the amplitude 1 over m Planck to the 4. If you want to do instability rate per unit time, per unit volume, that should be dimensions m to the 4. The only thing you can do, put a cutoff on these guys for external lines. Which is a bit weird because usual effective field theory implies cutoff on loops. Here, you would need to say that you break Lorentz also in UV, and you introduce a cutoff on this external momentum. Okay, and this is kind of not a standard procedure, but that allowed to Jim Klein and company to estimate the rate of such a process. You see, it's strongly UV dependent, but can be small. But that only happens if you break Lorentz, because if you don't break Lorentz, you integrate over all boosts, and suddenly, because Lorentz group is not compact, you will get infinite rate, which doesn't make any sense. That implies that the perturbative analysis is not correct. Okay. The interesting thing is Jim came back to this issue this year, and he published just 2 papers abusing this production mechanism now for dark matter, which is quite surprising for me. Okay, now how the instability works. So imagine you have normal degree of freedom, then this degree of freedom, which is Gaussy, and they conserve the total energy, of course. Time passes, the scissors opening up, because the Gaussy matter decreases energy, normal matter increases energy, total energy stays constant. And of course, this opening up, you start to explore more and more and more of phase space, okay? And that can go contrary to scissors without any limits. So that's the bad thing about that, okay, there is nothing, no quantity which bounds you in the phase space, usually. And that implies that it all depends on the interaction, on this nail here, okay? Good. So now let me illustrate it. How unstable can it be? Take normal oscillator, take this ghosty oscillator, let's couple them into quartic way. And you see, for some reasonable coupling, okay, it's not small, by the way, as you see, it's 4. The instability happens, it's like parametric resonance, actually, and it happens, this is log of the energy of the first guy, and it happens quite quickly. So during 15 periods, as you see, that starts growing, and then after that, the code would crash because it's too much. But what is interesting is that you could decrease the coupling constant. And by the way, here initial conditions are like similar to vacuum, okay, like vacuum fluctuations. Here, you can wait up to 600 periods. But then this instability starts, it's the same pattern, and it's really horrible instability. It starts really rapidly, and then the whole thing will crash again. So what is important is that in such systems, this instability can kick exponentially far away in time, actually. And that's what undermines the studies of when people do numerics for such systems. Because people do numerics for some initial data, you cannot do numerics for all of them, right? You study some initial data, you wait some finite time, and then you don't see big changes, and you think that the system is okay. In reality, wait longer, and it can explode like a bomb, okay? Good. So now what we suggested in 2021, it's a stable model where we can show analytically that it's all stable, not numerically, but purely analytically for all initial data. That, by the way, gives us hope that one can quantize it properly, and that's what we are working on. Okay, so basically, let's take Hamiltonian. Now it's normal oscillator, ghosty oscillator. Let's introduce interaction between them. And this interaction is kind of not pleasant. Later, I will show you a bit easier one, but it's not horrible. So you see, it's just some coupling constant, and then you divide by the square root. So you see, it's a normal analytic function. Nothing bad happens to this function ever. And what is important is this interaction is bounded. And that's, of course, kind of a bit drawback, a static drawback of this model, even though, as you will see, it's not needed, as we realize later. So in this potential, you can draw total potential. It looks like just one saddle for lambda less than 1/2 absolute value, or just kind of two saddles, kind of funny shape with lambda larger than 1/2. Now you can expand it, and as you see, this saddle can actually be stable, linearly stable, what's important. Not that normal linear stability only works under the assumption of positive energy, kinetic energy. So therefore, you cannot use it immediately here as a proof. So you can see that this saddle or these two saddles are kind of linearly stable, okay? So now the question is, are they stable not only linearly, but in general? You can see numerical solutions, they're not very interesting. You see some things just oscillating, rotating, whatever. It's in X, Y, it's kind of Lissajous figure. You see all this like they're moving. And then they will cover whole space, In that sense, maybe one should call it ergodic, I don't know, in some sense, because you see on average, inside of this volume, the trajectories will cover everything. But I'm not sure we can prove it. So naively, that looks stable. Okay, the question is, can one really prove it? And the proof is actually relates to this kind of black magic. Okay, by the way, I have taken this picture in a castle not far from Prague, which belonged to notorious military commander. As we are now seemingly entering ages of wars, we should all reread the history of 30 Years' War. So this guy was one of the most important military commanders in this war, and he also liked black magic, and he also liked horoscopes. And horoscopes were provided to him, by whom? By Kepler. So he was well, informed. So I'm not sure whether this drawing is not from Kepler, by the way. That's an interesting thing. So, but let's rely on black magic. So what will be the black magic is actually another first integral. So we have energy is conserved, but there is another first integral, which looks okay, like this, where k is, if you want, hyperbolic rotations. I want to prove that this integral of motion is, this expression is the integral of motion. So it's conserved on all trajectories. So How did we come to this example? Yeah.
When you first find this and then
Yes, absolutely.
Find that from.
Absolutely. Andrew, I will explain what we were doing. So in reality, you see just a second that one can obtain our system via complex canonical transformations. Okay, so what we are doing, that's what I call power of imagination, because we started to use imaginary units. So what we have done, we have taken an example introduced as we thought by this gentleman who is Darboux. And for you, it will be more clear what does this abbreviation mean, right? I think this one is Fellow of Royal Society, and then some other abbreviations. Exactly. So that's Darboux, but it turned out that actually that was introduced earlier by Lyapunov by almost 50 years before. And so basically, they were studying class of models which are integrable, which would have an integral of motion. And now there is a like quite vast literature on that. And we took the example, we have done complex canonical transformation and went to, again, real values. Okay, so that does not kill the integral of motion because the whole commutators of Poisson brackets remain. Good. So, and then using this first integral, it's very easy. You just look at the structure. This epsilon is just, you see, if you want a square of a radius in the phase space plus this positive expression, and then you see that this guy, due to the form of this interaction, is bounded, as you see from here. And because it's bounded, we can always see that this E, this integral of motion, lies between these two values. So this sigma minus absolute value of lambda and this sigma plus absolute value of lambda. Now it's super easy. We apply it to initial moment of time, that is inequality. We apply it to whatever later moment of time. And now we compare, because this E is the same, it doesn't change the value. That implies that this guy is less than this. On the other hand, it implies that this guy is larger than this. So in that case, we have proven that this sigma, which was larger than the radius square of the radius vector, right, is located in the square of the radius vector plus correction before minus this thing plus this guy plus this thing. So if you want, it resembles this toric. Okay, so you are living in a kind of onion shell in four-dimensional phase space, and you never leave it. So basically, I fixed initial data, and after that, I would know where the system evolves. It's kind of not necessarily that thin, but kind of thin piece of onion in four-dimensional space. Okay, so that implies that we have proven that for all lambda, the motion is actually Lagrange stable because we have analytic proof for that. Perfect. So now you see that's what is called Lagrange stable, and now we can also show Lyapunov. Yep. Sure.
Was that
Plots, numerics. Okay. Yeah.
Those are analytical?
No, they're numerics. Analytically, we don't know how to solve it because formally speaking, it's integrable, but to take this integral would be even harder than to solve it numerically. Yeah. Of course. Exactly. Yeah. As we see, we run this to 500 periods of evolution, but the point is we have analytic proof that it's the case. As you see, the motion is bounded. These are the borders, or if you want, the borders of the crossing between H and the second integral E. And that's what gives you finite space. In reality, you could think that motion in finite space, in configuration space, if everything is analytic, should imply finite also phase space. But that's a bit harder to prove. But you see, so what we have is true phase space proof. That's a good thing. Then you see, after that, what we can do, it's pretty standard stuff. We can use what Lyapunov introduced in his thesis. By the way, also, you know what unites Lyapunov with Lagrange? Both of them were married with their cousins. Really? Okay, good. That's actually, yes, that's quite surprising. But you know, actually, what is really sad, this guy committed suicide when his wife died. And he committed suicide just, I think, next day or something. And then he died in Odessa 3 days after his wife died from tuberculosis. So, you know, he was very sad always. So the point is that now this second integral of motion can be used as what is called Lyapunov function. And by the way, thanks to these Lyapunov functions, we can have guided missiles and all these fantastic things which we now use to kill each other. Good. So the point is what we can prove that at the origin, this E is just 0 if we check for the origin. Then it's clearly, you know, when this lambda y squared minus x squared is positive, then this E is larger than 0. And then one can see that when this guy here is less than 0, then nevertheless E is larger than this expression. Okay, and that implies that if yx and so omega x and omega y are normal positive frequencies, in that case for lambda less than 1/2, the origin is Lyapunov stable. Okay, so basically that's analytic proof. This is Lyapunov function by second tensor of stability. We are done. Okay, good. And interestingly enough, it's nonlinear stability. What is important? Okay, very good. So now, you know, because we have done an imaginary canonical transformation, one could ask, okay, it's all kind of analytic. Maybe it does not matter because we also got used to weak rotation and all these things. Let me show you that it does matter. Let's take a very simple example, p squared divided by 2, and potential will be hyperbolic cosinus. All right, very simple potential. Clearly, this is phase space. All these trajectories are just closed trajectories, and that's it in phase space. Now we do complex canonical transformations. And what is very important, if we take initial data, as people usually forget to do, the same as before, so if you transform also initial data, then of course, here we would need to be forced to use complex initial momentum and initial coordinates, then nothing would change. But we use real, and therefore the whole thing changed, and that's the result in phase space. As you can see, here the trajectories are closed, but if you go beyond this blue line, because clearly this is cosine, it just overcome the potential barrier, and it will fly forever outside. Okay? So that implies that Lagrange stability does care about whether you have done this or not. Now, let me tell you in the next, whatever, 10 minutes, do I have 10 minutes, right?
Yeah.
So, about our second paper, and there we thought that maybe we could introduce nicer models or much larger class of models. So actually, Liouville studied the model where here it would be plus, and there would be potential, which looks like this, roughly speaking, where U and V are these two expressions, and R, in his case, would be, of course, plus. And so you see, these are simple sets of coordinates, and it turns out that such a model for arbitrary functions f and g is integrable. Okay, that's a very interesting statement. And such coordinates actually called elliptic coordinates for proper r. I mean, when here it's plus, and they're very important in the series of integrability because, for example, Arnold's book dedicates a whole chapter to that. Okay, C is a constant. It's a constant which has dimensions of this, length squared, and it's just a free parameter here. Very good point.
You only have squared and squared
No, because you see, what we want at the end, it will be that C is larger than 0, and therefore this root is manifestly positive. It's already after the transformation. No, I'm deriving. So you see, it's exactly, they're arbitrary, but then the conditions for stability for such a model, which we derive, are the following: C here larger than 0, F and U are bounded from below, and then another thing is that F and U for large values of U and V should have this asymptotic, so satisfies this inequality for powers larger than 2. So F0 and G0 are positive constants. So that's what we derive in our paper. And I will just explain you how does it work, what is it. It's actually quite a simple exercise, I would say. So what's the reason? The reason is against this black magic. And the point is that's another first integral which is conserved. Has this structure. Again, the same k as I use, kind of hyperbolic rotation momentum, plus this kinetic energy. As you see here, C should be positive in order to keep this kinetic energy positive. And then interaction potential. So this is a structure. Of course, you see these are all in quads, right? Because this is not my Hamiltonian. This is just another quantity which is conserved. And the interaction potential here looks like this, okay? If you want this potential energy. So this is the key of this black magic. So this second integral of motion is conserved, and the conditions which I proposed in the previous slide or presented, these conditions imply that this U grows at infinities, so it creates a potential well for you, if you think about this guy as an energy. And on top of that, it's bounded from below, so therefore they're minimum. And these two conditions are enough. Think about normal potentials, that's how it would be, right? Sure. Wait. Oops. Oh wait, so that's too far. Yep. Are constants larger than 2? Yeah, the larger than 2. Yeah. Exactly, because otherwise, in some direction, we were not able to prove that this potential is not flat. And if the potential is flat, and this value you can propagate to infinity. I mean, this U potential. Shall we?
Somehow it's just simply greater than or equal to that.
Yeah, but then it's harder to prove because you see in the paper we provide analytic proof. Basically, these conditions are needed so that this U is unbounded from above at infinities and it's bounded from below. That's basically these two conditions what we need to have. Okay, now let me illustrate. You know, this looks not much better than what we had before. It's a much larger class, of course, but it's still some complicated potential. And the question is, how contrived is this potential? And again, think about the system that it has kind of this quantity. If it were energy, you would not be surprised that it's stable if I said everything about this potential, so to say, bit, right? Okay, so now what's the point? The point is that what we have proven in this horrible class of systems, one can write f and g as the same power expansion, okay, as the same polynomials, with the same coefficients Cn. In that case, this potential looks like this, and surprisingly, this corresponds to polynomial interactions and x and y. Okay, so now what we have proven there is that the first option, which is stable, Lagrange stable, is n equal 4 here, and it's given by this formula. Okay, it's a bit long, but it's not that bad. So this guy is a harmonic part with arbitrary frequencies. This guy is a quartic self-interaction, which is somehow related to these frequencies, but then there is this C which appears. Then another quartic interaction with a different constant, which comes from here, and sixtic interaction. So the sixtic interaction is the key. Without the sixtic interaction, we were not able to prove anything. It does not mean that there are no stable systems, but just we don't have a proof for that. So then the point is this sixtic polynomial interaction results in potential energy in quads of this first integral, which looks like this. And then immediately what you can see is that if I choose this C4 from here to be positive, then these guys, and C is positive anyway, so these guys give me just a rise of this potential well at infinities. Okay, so therefore I stay trapped in this potential well. Okay, so now let me show you how this potential energy can look like, and this is actually above at some logarithmic scale, you know, which I have done to just illustrative purposes. This kind of complicated surface As you can see, there are 4 minima, actually 5 minima, because this black guy is origin is also a minima. For some other values of parameters, it can be 3 minima. Here it's kind of in logarithmic scales, and here it's zoomed. Okay. And then you can basically normalize your frequencies to these parameters C4 and C squared. And from that, you would see parametrically in which cases, now in terms of these capital omegas, how many minima would you have? Okay. But think that minima of U are actually what one can show that they are saddle points of V. Saddle points of V are fixed points of evolution, and therefore these are stable equilibria. So they're not stable because they are saddle points of V, but they're stable because they're minima of U. U is potential energy, quote by quote, and then that's sometimes called Dirichlet-Lagrange theorem. What we all know, if you sit in the minimum of your potential, you are stable. Okay. So what is actually really hilarious regarding this system is this statement, that you would expect that you start interacting with the ghost and the whole thing goes astray, right? It goes crazy, just like completely start to explore all phase space, it's horrible instability. In reality, what happens if you take this potential I showed you before, you make kind of symmetry breaking, and instead of your original vacuum, which kind of still a vacuum, you introduce here 4 more vacua, and here 2 more vacua, and there's the most stable configurations. Okay, so there true Lyapunov stable points because this function J now is again a Lyapunov function. So it's the same thing as to bind this whole motion, right? So basically, it's kind of funny situation. So interaction with ghosts provide you new stable configurations. Not always, because, for example, if you are here in this white region, still the only point which is stable is origin. But if interaction is stronger, in that case, there is symmetry breaking, and you have this pattern of new stable points. Okay, just to illustrate how the system would move, it's kind of similar pillow structure as before. So this is the boundary which corresponds to crossing H and the integral of motion. And as you see here, so Marina was asking whether the system is ergodic. I don't know, because you see, we waited here just for 300 periods. And it kind of looks that some parts are not covered, as you see here and here. And to be honest, I don't know whether it will persist to be so or not. So if everything is covered, then it's ergodic. If it's not, then it's not ergodic. Okay, and you see, interestingly enough, Lagrange stability does not imply Lyapunov stability of some given solution. In reality, you can choose, let's say, frequency of a ghosty guy to be -5. In that sense, it's a tachyon, right? And you would think that, okay, this system is kind of, in the origin is not stable. And however, nevertheless, the total dynamics, you see, it's kind of very strange. The time goes to white, and it moves in a very, very complicated fashion, okay? But it is stable in the sense of Lagrange, so that you just remain bounded in this original kind of shape, which is given by initial data. Okay, so now you can ask, okay, you found such an integrable system, but is it physical? In reality, there is a great achievement of humanity, what is called Kolmogorov-Arnold-Moser theorem, and that tells you the following. Take integrable system. Suppose it was moving in a stable fashion. Take another system which was stable. Introduce interactions perturbatively, so that you think that the interaction is small, structural. And now, Kolmogorov-Arnold-Moser theorem will tell you that original integrable systems are moving in some tori. This interaction will just deform the tori, but up to measure 0 solutions, everything will be stable. So that's the interesting statement. So basically, these trajectories which were going around tori, the shape of tori change, but nothing else changes. Okay, provided the interaction is small. So therefore, if you want, couple to this oscillator in a small fashion, and it's all good. So some measure 0, you see, as far as I understand this, the statement, They are measure zero solutions which don't need to live on tori. They jump from one tori to another. But it's really measure zero. It implies that you cannot find such initial conditions. You would not see them, even numerically.
Does it mean that in order to find non-negative solutions, you have to do some constraint?
I would say vice versa. Vice versa. I mean, like all measure non-zeros. Basically, numerically, you only see solutions which are measure non-zero.
Yes.
Because numerics does coarse graining for you.
Unless you do not.
Yeah. Yeah, mathematically would find it all. Great. So you see, small structural changes or interactions with something else would not jeopardize the stability and finiteness of motion.
Let me just connect you with
Perfect.
They are measuring. They test how stable are these simulators that have to be for numerical simulators.
Perfect. Perfect. Okay, so after saying that, I have my finite slide practically. So why have not we seen such systems of fine nature? Usually, the standard argument says that, okay, these things are unstable, but there are now plenty of examples, actually continuum of examples, if you want, which are stable, okay? It's only in mechanics, we neglected gravity, maybe gravity doesn't like it, I don't know. But I think this is an interesting question, and it opens us a very interesting perspective, you see, to a hidden gem. Maybe Masato would recognize. It's a nice place in Kyoto, and you see it's a fantastic hidden path to tranquility, if you want. So thanks a lot for attention.
So we have time for questions. Are there questions for Alexander?
Yeah, the last question, the last statement. Why have we not seen this systems in nature? Can you elaborate why? Where would be one example?
Maybe simplest one you see the standard zoo of series would be like some condensed matter, right? That's the first area of suspect where I would try to find such things. But I'm not aware of any similar systems there. And of course, usually there is a prejudice, like people would not try to model anything what they observe with such systems.
Yes.
So
there is a big, I think that we have a challenging in physics. Classically, John Hopkins found very much like that. What you are describing.
Oh, that's great. Not
the
really.
real butterfly effect.
Okay.
The second paper, which is now being investigated. Because it is normally in positive energy.
Oh.
It's really very, very
Okay.
challenging ideas for
Cool.
together with the astronomers that
It's very important to model Navier-Stokes correctly. Every time I fly, I think about it.
Yeah, well, yes. No, I think what how it works.
Yeah. But maybe if you fly on an airplane for 1,000 years continuously, then suddenly.
Yeah, or you specify your
Yeah, but for God's sake, engineers, they take it all factor 5 or 3 more, right? So it's good. Yeah, we're thinking about it, but I don't know. Absolutely, absolutely. So now with this, you see, with this polynomial potential, I'm sure one can arrange it. It should be possible. I'm sure it should be possible, though I cannot tell you particular example. It would be great because that's what open us analog ghosts or whatever. It should be still interesting because it's related to positivity of energy and kind of the cornerstone of our existence.
Any other questions or comments?
So your work on the connection to gravitation is to say that one can consider actions with ghosts that may be relative.
Yeah. But you see what we can. Okay, let me tell you a bit more. So we started to look at mechanics because it's better to look at discrete number of degrees of freedom before going to an infinite number to continue with those. Then actually we have now numerical simulations without analytic proof, unfortunately. And there we also think that everything is kind of stable. But the point is, you can trust the numerical simulations up to this moment of time and up to this precision. You would never know what happens like much later. But we see that even in field theory, things can look stable. Then the point is, if we start quantizing field theory, that's where I don't know how to do it, because you see standard prescription of Lorentz invariant vacuum and attempt to integrate all boosts create your infinite rate. So all this technique of perturbative calculations breaks down, and then it will be very strange because you see, naively, perturbation theory suggests that the instability is super strong. Super strong means like large particle number produced. Large particle number should be classical. Classically, then I should see it. I don't see it. I don't know. But it's interesting to understand what can happen, especially in gravity. In gravity, of course, we all know that the total energy in bulk is just zero on all solutions. So it's all only on the boundary. And then it becomes much more interesting, actually, how to understand what's happening there. So we don't know. The answer is we don't know. But we thought that, being motivated through gravity, maybe we could say something more on just simple systems, and then we will increase the level of complexity.
Yeah, one of the interesting results of this was that they found to calculate numerically the merger of three black holes. They had to specify the initial conditions to receiving a flyer in the planet.
Ooh.
Yeah.
Okay, that's so that's an analytic result, I suspect. No,
Numerical.
numerical.
The numerical gravity is the orbits of black holes merging, and you won't get a result unless you specify the initial conditions.
But that's a very important result, right? Because that implies that three macroscopic bodies, due to the chaos, they depend on quantum gravity, right? Well, I was not aware. I definitely need to look at it.
Great. Looks cannot be right.
Don't know.
Okay.
You see, I'm very surprised. I'm very surprised, but
Very surprising.
I don't know.
I think it's a property of the
Right.
It's not more of it, you don't have. They use
No, that's it's fascinating. What can you say?
Degree of accuracy, what the by very narrow range.
So it's an ultimate butterfly effect, in a sense.
Yeah. There's two kinds of butterfly. Yeah.
But maybe, you know, if you start looking at environmental effects, some accretion of some very tiny portions of gas and so on, then you average it, and this whole like thing kind of becomes more robust and.
It's just funny. I just wonder what. We actually have now quantum mechanics model based on the same principle with the years for Vikman or something.
Yeah.
It's interesting at the classical level for even.
Interesting.
Right.
No, of course, it's fascinating. What can I say?
Right. Any final question?
Very short and not very relevant comment. I just found the basic features that Lyapunov from Prague, and indeed it seems to be from
No. Lyapunov was not from Poltava. It was Strogarsky who was from Poltava. Lyapunov was born in somewhere, I have forgotten, somewhere in Russia, but then he studied in Kharkiv, and there he wrote his. No, Lyapunov was not. Yeah, no, but it's important. No, history is very interesting.
Very good. Well, let me stop the recording. So let's thank the speaker.
If you enjoyed the video, like and subscribe.